My name is Carolina, and I'm here to help with another experimental demo.
And this one is on torques, which we've covered in the book under equilibrium. What we have in front of us is a meter stick. It is more or less balanced on a pivot. The reason that it is not exactly balanced is because of air currents. But if we were to suck all the air out of the room and have a vacuum in here so that it would work, we would not be able to breathe. And that is a minor setback, if anything. A major setback, right? We need oxygen. Okay, there it goes. It's on the other side like that. I think the Blue Piggy once owned this. I don't know. At any rate, we're going to hang weights, masses actually, on each side. The masses are going to be given to you in grams. And you can convert that to force by multiplying the grams by 980 centimeters per second squared, which is a little g in the CGS measurement system. So 2 grams would be 2 times 980 centimeters per second squared, or nearly 2,000 dynes. The force unit is not newtons, it's dynes in these very small measurements of centimeters and grams and seconds. So the force unit is known as the dyne, and that is how we do it. Now what we're going to do here, this is more or less balanced, which means that the riders, which are already on the meter stick, are about equal distances from the center, from the fulcrum. And look at that, it's almost balanced. Yeah, look at that. So we got it as close as we can as far as the air currents are concerned. And we have some slotted masses and hangers to put them on and all kinds of good things. Now, the first thing we're going to do is understand that the meter stick has mass itself. And what was the total mass of the meter stick? It's up there. 133.8 grams as measured by Carolina. And that is accurate. So what you're going to have to do is figure how much of that 133 grams is on each side when you do this. And we're going to assume that the right-hand side of the meter stick is 53 centimeters or 530 millimeters long. And the left-hand side, because of where it balanced, is 47 centimeters long, and which is 470 millimeters. So now you have the lengths of each ruler, and you're gonna have to average that in to get a center of mass for the right-hand part of the meter stick and the left-hand part of the meter stick. You're going to have to treat the meter stick as a massless stick, and the weights are hung on it. But as you know, it's not massless. All parts of the meter stick got mass. So you're going to have to find the center of mass of the right-hand side and the left-hand side. Follow the diagrams in the lab information packet. And you're going to need to factor that in and treat it as a third and fourth mass, actually, a point mass. Okay, now let's take the weight that's on the left end and move it in closer. Yeah, right there is good. And we'll tighten it down. Now, on the long end of the meter stick, we're going to put the little hanger, and we're going to attach a 1 gram slot.
5 grams.
Mass, right. Oh, it's 5 grams, okay.
We have 1. You want to do 1?
No, 5's good. I like 5. The total amount of mass is that 5 grams plus
another 5.
Another 5 for the hanger. Okay, and then the thing the hanger hangs on is 16.8 grams, right by your shoulder there. 16.8. So the total mass at that point on the meter stick is the 16.8 plus 5 plus 5, okay, which is 26.8 grams. Okay, and what is the distance, Carolina, from...
The distance is 280 millimeters.
280 millimeters between her fingers, from the fulcrum or the balance point to where the mass is hanging. And we multiply by little g, by the way, so that you get a force, you get a weight in dynes and not just a mass. All right, now let's go to the other end of the meter stick. And I can see if I can zoom in on there. If you can tell me the amount of mass you're going to have to put on, it's an identical 5-gram hanger, and thing that the hanger goes on, 16 grams or so. And now you're going to hang a 20, aren't you? That's a 20-gram mass, slotted mass, onto the hanger. Does it balance with just 20 grams on there?
Nope.
All right, now we're going to start adding. Oh, no, it doesn't. 20 is too much, isn't it? So let's go down. Let's start experimenting and put less mass on what you're viewing as the left-hand side of the stick.
We'll try 10.
Well, we'll try 10. All right, 20 don't work, 10 will. We want to go lighter there. I thought we were going to have to go heavier. No, we're going to have to go more than 10, aren't we?
I would go by ones, though, because it seems very close.
Oh, okay. Whatever works.
What do you think?
Yep, just the way you would use a balance, which is what this is. You keep putting little weights on both sides until you got it more or less equal.
Maybe I should have used the 5.
Maybe.
Ooh.
Too much?
No, not doing anything.
Oh, now we go.
10's
Now
too much.
10 is too much. So I would guess it's in the upper teens somewhere.
Let's see.
Ooh, we're getting closer. 1 more gram on the left might do it.
That one's 2.
That's
so
2. Okay, 1
much.
gram. 1 grammy.
Let's see here. Here we go.
1 gram. Oh, it's too heavy. Okay.
Let me try one thing.
Okay.
Take off one of these ones and put a 2 instead.
Yes. By the way, a penny has a mass of 2 grams. They make them that way. And a nickel is 5 grams, actually. Couldn't remember, it's 2.5 or 5. But you can look it up on the government website, Treasury Department.
It's still heavy.
It's too heavy on that side, huh?
Try
1 gram.
those are 2s.
Mm-hmm.
It's close.
I should get on the left side. It'll pull it down. What I do with the doctor's scale is I use my cane, I push down on the floor, and that changes the mass, or at least what it looks like.
None of these are working. Try this. Oop. Let's try this. Even with the 10s. 10, 12.
You took off a lot.
Yeah.
Okay.
That's only adding 1 more.
Okay, how much is the total mass you got now? It was very close. Yeah, okay, let's call that balanced. How much mass is
Pretty
there?
close.
How much mass? Our audience is probably getting impatient, so we're going to...
5, 10, 22.
22 Grammys, plus the 5 of the hanger,
Yes.
plus the 16.8 of the thing that goes on the meter stick there above the hanger. So that's what we have. Now what I want you guys to figure out at home is what is the distance between the pivot and that hanger. Can you show that, Carolina?
Right here.
That distance right there. You know the right distance is 280 millimeters So what's the left? You know what the mass is required to balance it, which was how many grams again?
22.
22. Oh, I'm not on you. 22 plus the mass of the rider plus
The mass of the hanger.
The mass of the hanger, right.
I just want to keep playing with this.
You do. It's addicting. Yes, it is. It's frustrating when you can't get it to...
Exactly.
Exactly. But just think, the students that come in here for the lab have to do this and get it exact, and it drives them crazy. It does drive them crazy. Now, where does this...
22 is close, though.
Where does this become very important, do you know? I mean, in all fields it is.
Yeah.
Diamonds.
Immediately I thought about a seesaw
Diamonds.
and children on it.
Diamonds.
Diamonds?
Yeah, diamonds. Diamonds. Oh, they're cool. A carat is 1/5 of a gram.
You're right.
So a 5-carat diamond is 5 grams. Yes, it is. If that was a... take a 5-gram one.
I think there's one right here.
Okay. And what we'll do is show it... What is it made out of?
The 5-gram one is this one.
Okay. It's aluminum, right?
Yep.
Let's show it. That would be a 5-carat diamond if it were diamond. Same amount of mass.
It's not, unfortunately, a diamond.
Yep. So I will zoom back out. I'm doing this by hand, so this is not working. Something with my camera here. We'll get it working. Just bear with me. There we go. Had a little malfunction with the camera. So now we've learned a little bit about equilibrium the hard way, how difficult it is to do in the lab. And what you do is all the torques on the right, the force times the distance, and all the torques on the left should equal. So what you've got right now is you have got the distance for the right, you've got the mass hanging on the right, which you convert to force by multiplying by 980, and then you've got on the left, you've got the mass on the left, which you convert to force by multiplying by 980, and then what you don't have is the distance from the fulcrum to that mass on the left, which you're going to figure out. And again, I'll put the formula up here in the exercise that this link is on, and directions of how to do it. So thank you for viewing the demo, and Carolina.
See you next time.
Okay.